All right, here we go. So today we're going to talk more about the imaginary homework, about making the complex class and the imaginary class, and the complex class uses the imaginary class and all that stuff. But before we get into that, we have to really understand why we go to the effort of putting things into different files and all that stuff. There's a tendency with some people to just put everything into one file. And that works fine for small projects, honestly. But what happens is that when you get into bigger and bigger projects, when you've got 300,000 lines of code in one file, it takes a really long time to compile. And so one of the things that we optimize for when we do projects like for realsies is we try to optimize the compile time down. We try to make it able to compile really, really fast. And anything that takes more than, I don't know, 3 or 4 seconds, it kind of breaks your flow. You know, what you want to be able to do is make a change, write a little bit of code, save it, compile it, run it, and immediately see, you know, what's happening, what's going on, then immediately get back into writing the code, write some more code, run it again. And when you get into big, complicated programs, like a lot of times, if you ever wonder why there's cheat codes in video games, that's because if you're the person making Skyrim, let's say, you don't have time to replay through the entire game to find out if this one quest is working correctly. You know, let's make a new character and start in Helgen again. No. Like, you immediately, you know, you probably load a saved game, but if you don't have a saved game, then you enter a cheat code, set my character to this level, set this equipment to this, teleport to this location, go. So that you can get on top of the testing immediately. So you make a quest, and then you test the quest. And you edit it, you test it. You're always working. You're always active. And part of that is just having a good, fast compile time. Okay. So we're gonna learn today about how compilation works for realsies, right? Like on real projects, how they're set up. And yeah, you didn't know that about video games. Yeah, that's why cheat codes exist. They're rarely for players, although, you know, some of them are fun. Like in Age of Empires, you can spawn, you know, Viper cars that shoot bullets at people and things like that. You know, kill the enemy knights with your Viper. But yeah, mostly it's just so that they could test. You know, they're testing things. See you, Mr. Bitter. You know, or you go into invincibility mode, or you turn on no clip in Doom or Quake so that you can run through the walls, so that you can look at the level and things like that. Okay. So GTA codes are examples of codes just for the player. Yeah, I mean, nowadays, like, there's kind of an expectation there will be cheat codes in games like that. But really, just like speaking broadly, like the reason why they exist is so that the testers of the game themselves can quickly, you know, stick their head through the wall and look around and see, you know, if everything is in the place where it needs to be. Okay. So, first of all, what does hashtag include do? So when you have the hashtag include, pound include, what happens is that it copies and pastes that entire file. And this is not a good system, by the way, incidentally. C++20 is finally out, and they introduced modules, and modules are sort of the better way of doing header files. But we're not learning about that today, also partly because they're not fully implemented and nobody really knows how they're exactly going to work. So that'll have to be a lecture for another semester. So hashtag include, though, all it does is if you say hashtag include iostream, hashtag include read.h, whatever, what it does is it literally copies and pastes that entire file into your file. That's all it does. It's not like in Java where the system is a little bit more sane. It literally is just copying and pasting the entire file. So if you've got main.cc, and main.cc includes imagine.h, and main.cc is also probably going to include complex.h, And complex.h is probably include imagine.h. Then when you do all these different includes and all these things gets copied into main, if you actually look at the results of the preprocessor step, all the stuff, when you hashtag include iostream, all of iostream appears at the top of your main file. And it gets very, very big. It can actually slow down your compilation time. But a header file is typically much smaller than your implementation file. So a header file is typically much more compact. A header file is typically just a list of functions and classes. So a header file typically is just like, hey, these functions exist, and they're out there somewhere. That's all a header file is. And so you can include a header file much more quickly than you can include a implementation file. An implementation file is a file that actually has your code in it. So right now you guys have been working on imagine.h and imagine.cc. Imagine.cc is your implementation file. Imagine.h is your header file. And your .cc file is going to be much bigger. And so it's faster to just include the header file. Header files, since header files can get included multiple times, like main.cc could include imagine.h, and it could include complex.h, and complex.h could also include imagine.h. There's a possibility that you might end up including the same file multiple times, and that's bad. There's something called the one definition rule in C++, where something can only be defined one time. And if you try defining something multiple times, then C++ gets mad. And so if you try ever making a variable with the same name, or if you try making a class with the same name, then C++ gets mad at you. So what you have to do is you have to put on the first line of your header file hashtag pragma once. What that means is that if main includes this file and then it includes somebody else that includes that file, like string will get included all sorts of different times. If that, because you could include string from just your main could hashtag include string. But if you include iostream, that'll also include string to get the string class, to have strings. That's not part of the core language, by the way. It's part of the standard library. And then if you include my read library will also include iostream and string. And so all of these header files could get included in different paths in different ways multiple times. And so it's really important to have hashtag pragma once on the first line of the header file. What that does is it tells the compiler, if I've been included once already, don't include me again. And it stops C++ from getting upset at you for having the same class redefined multiple times. That's technically not it's technically not part of the standard. There is another way of doing it, which I'm not going to tell you because every compiler supports pragma once, and anybody who tells you not to use it because it's not standard has never used a compiler in their life or something. I don't know. I'm being sarcastic, but literally despite pragma once not being part of the standard, every compiler supports it, so use it. It's better than the alternative. Okay, so here's what it looks like if all we had was our imaginary class, right? So you got your imagine.cc, you got main.cc, both of them are including imagine.h, and this would get more complicated if we threw on here complex as well, right? Because you've also got a couple more files in your homework assignment. You've got complex.h, the header file, main includes that. Complex.h includes imagine.h. And then there's a file over here, your implementation file called complex.cc. Complex.cc includes complex.h, which includes imagine.h. And so you've got 3 different CC files, you got 2 different header files, and you've got this like interesting web of dependencies, right? So if imagine.h changed, like if I were to change imagine.h, then this file would have to get recompiled, this file would have to get recompiled, and this file would have to get recompiled, because all these people use the imaginary class. So if I did something like deleting the plus operator from it, all of the people, all of the clients of that code would have to recompile. And that'd be unfortunate. So usually we don't change the header files very much. Usually header files are usually pretty stationary. Header files usually don't change very much. Usually it's the .cc files that change. You find a bug in your operator plus, you change the code for the operator plus. Usually the list of things you can do in your header file don't change very often. You will. If you like need to add a new operator or something like that, you'll add it, and then it'll trigger a full recompilation. But in general, most, like probably 80 to 90% of the time, you're doing your work in .cc files. Header files don't change as often. They're fairly stationary. Okay, and so if what some of you found was if all you do is type g++ main.cc, this actually won't compile the project. When you guys were working on your homework, I got Discord messages from people saying, I'm trying to compile the code and it's not working. And the reason for that, the reason why it's not working is because you've got code over here that is not getting included into your project. So you've got code over in imagine.cc and complex.cc. These are functions you need for your code to run, but if all you type is g++ main.cc, then you'll get what's called a linker error, and we'll go into that in a second. David Thompson says, is the other way the if and def thing? Yes. And the other way is by saying if not defined some constant, then you define it. Then at the very bottom of the file, you say hashtag indif. That's the proper way of doing it. I don't like the proper way of doing it because people will forget to put the hashtag at the bottom of the file, and it breaks literally everything. The only downside to Pragma once is that it's not standard, but given the fact that every compiler supports it, it's standard. And it's one line of code instead of three, and it won't hose you if you forget the closing indif at the bottom of it. So, yeah. And so, you could compile the code like this. This would actually work. If you compile the code like this, g++ star.cc, that will bring in all the different code from all the different CC files, put them all together, and it'll work. That'll make your a.out. It'll compile your code. But that won't work if you have multiple projects in the same directory, which is probably bad practice anyway. But there's a better way, and this is kind of the thesis for today, is that there's a better way of building your project. And the better way of building your project is by typing make. Make will handle that web of dependencies for you. So rather than doing anything manually, you're going to end up typing make for your project. And before we understand how Makefiles work, let's understand how compilation works. Okay, my code works when you type g++ main.cc and passes most tests, but doesn't work when you type make. That's unlikely because you have code in your .cc files, your other CC files, unless you've just merged them all into one file, which I don't recommend. What is the difference between a .cc file and a .cpp file? There is no difference. So back in the day, there was a language called C, and you would have like main.c. And then when C++ came out, they called it main.C. But then people realized these two things look pretty damn similar. And also there was an operating system at the time called MS-DOS and Windows 95, which was a thin layer on top of MS-DOS. And so MS-DOS basically kind of required a 3-letter suffix. And so if you ever see like readme.txt, right? The txt, 3 letters, or some Word file, .doc, 3 letters. The reason why there's all these 3-letter suffixes is because of MS-DOS. And since then, the world's moved on, and now we've got .docx, and that wouldn't work in MS-DOS. MS-DOS had what's called the 8.3 file name format. 8 letters for the file name, 3 letters for the suffix. Now, that's old history. But that's why main.cpp caught on, was because it was 3 letters, and so it worked with MS-DOS. I don't like typing extra letters. One of the things that I optimize for is my workflow. And so main.cc is 2 letters instead of 3. It's also faster to type. You can double tap C faster than you can type capital C, faster than you type CPP. And then there's also main.cxx, which is another thing. All of them mean the same thing. They'll all get compiled the same way. All of them are C++ files. It's just, they're all just equivalent options. I prefer that because it's the fastest to type. Okay, so good question. All right, so how does compilation work? So to compile a program, what does compilation mean? When you compile a program, you start with source code, and you end up with an executable. You start with source code, you end up with an executable. That's the big picture, right? You start off with C at hello world, blah, 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 and you compile it, and it goes from that text file for humans into a program that the machine will run, okay? Humans can't really read A.out. Really. It's, I mean, if you really worked at it, you could probably figure out what's going on inside of A.out if you were to look at it in the binary editor and stuff like that. But source code's for people, and the what's called object code and executable code is for computers. And to compile it translates from one to the other. So today we're going to learn where programs come from. Okay? So the you're including imaginary.cc and complex.cc. Yeah, don't do that. Don't do that. We're going to learn the proper way of doing that. Yeah, only include header files. And that's why we're doing the lecture today. That's why we're doing the lecture today, so you understand how to properly compile programs. So, so up until now, I've sort of not gone into this because it's a whole lecture. But when you work on real projects with multiple source code files, you kind of start needing to know actually how the process works. Up until now, most of our projects have just been in main.cc, and maybe we've included like one header file, like for fractions, right? But we're gonna learn the real way of building programs. And I mean, if you know, I'll just show you. Like so I've got the source code for the original Quake on here. Quake source server. So here's the source code to the Quake server, and here is the source code for the Quake client. And so you can see how many different files I have in there. I've got 196 different files. Okay, and some of them are .c files, is written in C, not C++. Some of them are header files, and some of them are asm files, which is assembly for increased speed. And yeah, and so if you look at a header file, like let's look at, I don't know, render.h, open with code. The header file just has class declarations, or like classes, and then it has just function declarations. You see this? All these functions here, it just says semicolon. It's got the function name, semicolon. And what that means is, these functions exist somewhere. Somebody has written this function. All you need to know to call a function is that it exists in C++. You don't actually have to have the source code to a function to call it. If you want to call a function, all you need to know is the name of the function, the parameters that it takes, and the return value that it has. If main.cc includes this header file, it could call r_init without ever actually having known what r_init does. Okay? All it needs to know is the name of the function, what parameters it takes, and what return value it has. That's called the function signature. And so a header file is typically just like this. It's just a bunch of, hey, this function exists, this function exists, this class exists, this class exists, this function exists. And so this is 152 lines of code. And if we go to render.c, is there a render.c? Interesting. Render.c, I don't see it. But the actual source code for it would be much more expansive, right? And so how do you manage all these things, right? You got all these different header files, you got all these different .c files. They've even got assembly files, which you'll learn about in CSci 45. How do you keep track of all of it, you know? And so how do you compile it? You know, it's an interesting question. And so, you know, they use Visual C++, and they have project files and things like that. But we're going to learn kind of the Unixy way of doing it. Okay, so, but in order to make any of this make sense, we have to understand what actually happens when you compile a program. Okay, so so when you let's just talk about compiling a single file. When you compile a single file, there's a number of steps that take place, and I'm not even going to get into all of them because a lot of them simply don't matter for where you're at right now. But there's still enough that matter to make it worth this lecture. Okay, so the first step that takes place is there's something called the C preprocessor. The C preprocessor. It does a pass over your code. Every hashtag include, the preprocessor copies and pastes that file into your file. So if you hashtag include imagine.h, it copies and pastes imagine.h into your file. And so if you have things that have like, hey, this function exists, now main knows that function exists, and it can call that function, even if it doesn't have the source code for it. So CMath might have a bunch of things like, hey, this function named absolute value exists. Hey, this function called pow exists. Hey, this function called square root exists. And it'll just be like, there's a function named square root, it takes a double, it returns a double. Semicolon. That's it. It doesn't have all the code that goes into square root. Okay. Hashtag define works like a constant, so you can hashtag define array size to be 100, and then anywhere within your code the word array size appears, it'll replace it with 100. There's macros you can do with the C preprocessor. I'm going to close the door. My daughter's teacher is really loud right now. So there's a whole bunch of deep and dark magic you can do with the C preprocessor. And most of it doesn't matter. The only things that really matter is hashtag include and hashtag pragma once and hashtag define, I guess. But you can use it to cut sections of your code out. Like there's a lot of really interesting things you can do with the C preprocessor that doesn't matter for right now. But anything you see that starts with the hashtag, the pound character, that's a preprocessor directive. It's not part of the C++ language. It is part of the C preprocessor. It actually, all that stuff takes place before the C++ compiler looks at the code. Step 2, the C++ compiler runs through the code, and it writes down a list of every class that it knows about. It writes down a list of every function it knows about, every variable. And so like if you say, you know, double x, then it's going to write down somewhere, okay, we know there's a variable named x and it's of type double. And if you do double xy, then it's like, okay. So it just maintains this manifest of every symbol that it knows about, every x, every y. If you have a function called foo, it's like, all right, I know this guy named foo, this is the parameters it takes, this is the return value it has. And so C++, just as it goes down, it just writes down everything that it knows about. And then every time you do something like x is equal to x plus y, it'll be like, have I heard of x? Have I heard of y? Yep. Is there an operator that takes a double on the left side and a double on the right side? Yep, it's baked into the language. Okay, this compiles. Check. Right? And so C++, but if you make a function call, let's say you make a function call to foo2, and it's never heard of this foo2 person before, compilation error. I've never heard of you. I've never met this man in my life. You know, Loki, right? You know, maybe you had a function named foo, and you just did something like that. You had a declaration for it, but you typed it in wrong. C++ was like, I don't know who foo2 is. I don't know what value it's supposed to be. Compilation error. It will not work. Yep. So as you go down, you know, you can just forward declare things like this. And that all that's saying is that somewhere out there, somebody has written a function called add that takes 2 integers and returns an integer. And as long as you do that, then you would be able to say, you know, add, you know, 3 and 5 or whatever. That would compile. Even if nobody actually wrote the function, it would still compile. Okay. You're going to get an error later on, but it'll compile. And that's why we always put hashtag includes at the top of a file. That's because that brings in all of these function prototypes. So the CMath library is going to have, square root, double, and absolute value. There's probably different overloads for int, absolute value, double. Like the CMath header is just going to be a bunch of lines like this, where it's just like, this function exists, this function exists, this function exists, this function exists. And then if you ever call square root in main, it's like, have I ever heard of a person named square root who's a double? Yeah, right there. So cool, it'll compile. All right. So your actual code will go into .cc files, usually. You could put everything into a header file, and that's called a header-only library, and that's what we did for fractions.h, and it worked fine, because it was a small enough project. You're not going to notice the... I've never met this man in my life. Yeah, Loki, right. For small projects, putting everything into a header file works fine. But for bigger projects, we typically split them into header and CC files in order to improve the compile time. Okay, so if you have multiple .cc files, then the compiler will need to will repeat that step for every .cc file. So if you've got, like in the Quake directory, I don't know how many C files there were, like 40 or 50. The first time you compile it, it will have to go through and compile every one of those .c files, generate object code is what it's called, and then it generates what are called object files, which is the compiled version of your code. So it goes from a text file to an object file, or object code, and that's what the compilation process does. When you compile something, it goes from human readable text into object code that your CPU can read. Your CPU accepts object code, and when you take CSI 45, you'll learn about this, but basically it's like, it reads in a bunch of ones and zeros. It says, okay, that's an add, and I'm adding this value and this value, and I'm going to store it into this thing here, and that's what CPUs actually understand. Your CPU understands object code. It does not understand text. And so what will happen if you have like 50, like let's say you have a.cc, and is there a difference between CMath and math? Yeah, there's a small difference. So if you hashtag include, if I could spell CMath, the difference between that and hashtag include math.h. This is the C++ version of this. This is a C header file. This is a C++ header file. And they're very, very similar, except all the stuff in the C++ header file is part of the standard namespace. So if you don't want to import things, if you don't want to import std abs, and you just want to import abs, that's the difference. So everything you include from CMath is going to look like this. It's going to be part of this std namespace. If you just include math.h, then it's not going to be part of any namespace, and you'll just call abs. And so if you don't like stds, you can include math.h if you'd like. Okay, so let's say you've got a.cc and b.cc, b.cc, and c.cc. What the compiler is going to do, if you say G++, star means everybody. It's a wildcard, all CC files. What the compiler does, it's going to turn that into a.o, b.o, c.o. Okay, and you're like, wait, I haven't seen those before. And yeah, it's because it erases them afterwards. If you want to keep them, I'll show you how to do that in a little bit, because there's a really good reason to keep them. But what happens if you just compile all the .cc files together, then it generates a .o file for each of them. And then the final step, step 5, the final step is all those .o files get put together into a.o. Okay? And so if that's when all of your promises come due. So if you've promised me that there's a function called add right here, if you've promised me this function exists, it'll compile just fine. It'll generate an object file just fine. But if you didn't ever actually write it, if you never got around to doing int add, int a, int b, return a plus b, if you never actually wrote that code, then when this step happens, when step 5 happens, when it puts all the different .o files together, there's a linker step, and the linker step is where it actually it's like a jigsaw puzzle. So if this guy was calling a function found in here, then it links them together. So okay, that guy is calling this guy, okay, cool, and that guy's calling this guy, okay, cool. So B's calling somebody in C, and C's calling somebody in A, and it's like a jigsaw puzzle, and it puts everything together. If, however, you did not ever actually write one of the functions that you promised existed and you called it, then the linker is going to be like unresolved reference. So you promised me there's a function called add, and you lied. You're a lying liar. You're a lying liar of Liarsville. And it will not generate the a.out. Instead, you will get a really weird error message called it'll be a linker error, but they don't look like normal compiler errors. They look ugly and garbage like. And the easiest way of getting a linker error is like this. Well, yeah, okay, we can do this. Int main. Okay, so this code here will compile just fine. Hello world, cool. Now, what if I mistyped main? What if I mistyped main and I called it man instead? When you compile your program, it actually tries calling main. That's the beginning of your program, right? And so if you try compiling it now, it'll compile, but it won't link. And what you'll see is a linker error. The linker is called LD. LD is the name of the linker. And it says this garbage long thing here, CRT, the C runtime system. See the .o file? This .o file is calling, it's in a function called start. So there's actually secretly a function called start that takes place before main. And start calls main. And it's trying to call main, but it can't find main. You promised me main existed, but it doesn't exist. And so you get an undefined reference error. And it looks really bizarre. It doesn't look like a normal compiler error. And if you ever get these things, that means you have a link problem. So you promised a function that you promised that there would be a function, and you didn't give it the function. It couldn't find it, so it could not generate an executable. So error LD, the linker, returned 1 exit status. Remember, if an error happens, it's normal to return 1, right? Exit 1. Another easy way to show a linker error, like let's call a function. Is that like STIENC? I don't know what that means. If I make a function called foo, this code will compile. Notice how COC cock is not complaining about anything here. That's because this code will compile. This code will fail on the linker step because I've promised it that there is a function called foo, and I'm going to, in fact, I'm going to output the value of foo. And this code will compile just fine. Sorry, I haven't seen Disenchantment. I didn't hear good things about it. So, yeah, foo here is a function. And all you need to have this code compile is the signature. Right? That's, that's the thing. Oop. What happened there? That's all you need for the code to compile. However, if I try compiling this, g++ main.cc. Whew, what's happening here? G++ main.cc. Then I will get a linker error. Linker, it compiles fine, but it says undefined reference to foo. You promised me there's a function called foo, but foo doesn't exist. Okay. Now, what if I made a function called foo.cc? Ah, damn it, there's already a foo.cc. Then Makefiles.cc. All right. Int foo return 42, 43. What's going on here? That's a bug. 42. Okay, so this is a different .cc file, right? Looks kind of, there's no header files, right? I don't need anything. Everything I'm doing here is just part of the standard library. I'm just making a function that'll return 42. Okay. And so if I try compiling Makefiles by itself, it won't compile because there's no main. And if I try compiling main by itself, it won't link because it doesn't have foo. But if I compile the two of them together, g++ main.cc, Makefiles.cc, then it will work. And if I run it, it prints out 42. Okay, because there is a list of all the different functions that things call, and foo is going to be in here somewhere. Yeah, there it is. And so it was able to find it. And so a U means undefined reference, but a T means it is found, and it is in the text section. Okay. Does that make sense to you guys? So I had one file. Why am I not typing right? Main.cc. So I've got one file that's calling a function. It doesn't have any idea about what's in it. Just all I'm telling you is that this function exists somewhere. And then over here in Makefiles, that's where the code is actually found. What is T again? Template? No, not in this case. This is I printed out all the different functions that are within the executable. And so T here stands for text segment. So that means that main is in the text segment, the code segment of the a.out. And so this is more CSI 45 stuff. You don't really have to worry about it. But the point is, it found foo. If I were to compile main.cc without foo, if I don't link in Makefiles, you'll see that it's undefined. See that? So by default, if I were to compile main.cc just by itself, then it has an undefined reference to foo, and that's why you need to compile main and Makefiles together, because main is calling foo, but it doesn't have foo. It's an undefined reference, and so you have to. It's a jigsaw puzzle. So maybe Makefiles calls a function in another file, and so you have to take all these different object files together and put them together. Okay, you have to put them together to make an executable. So so basically what happens is that for every .cc file in your project, it takes every .cc file and turns it into a .o file. And if you choose not to keep it, then it erases them afterwards. But if you want to keep it, you can do this. -C means compile, or separate compilation, or partially compile. There's different words for the same thing. But what that essentially means is keep the .o file. And so if I wanted, I could g++ Makefiles. Won't compile by itself. But if I do -C, if I partially compile it, it generates an object file for Makefiles. So if you look at it, I now have a .o file for main, a .o file for Makefiles. It generates these things anyway, it just normally deletes them. And then I can use these .o files to actually build the executable. So I can say g++ main.o, Makefiles.o, and this will do just the link step. So if I do that, then it takes those two object files, puts them together into an executable. You know, one .o file could have half your functions, another .o file could have the other half of the functions, they could be calling each other. And so in order to make an executable, you have to do this. You have to compile, you have to piece them together at the same time. But why partially compile a file? Great question, Miss Crump. The reason why we do that is because the hardest step, the most time-consuming step, is this one. That. Going from C++ into object code is the most time-consuming step. This step here, the linker step, is actually very simple. It's very fast. You can link even a giant program pretty quickly. Not instantaneously if they're really big, but pretty quickly. And it takes, you know, maybe a second on a big program. And so what's nice, Miss Crump, is that if you have 50 different, imagine you have 50 different .cc things. If you turn all of them into 50 different .o files, then let's say you modified just one of them. Let's say you modified just one of these .cc files. All you have to do is modify one, just separately compile one of them, and the one that you modified, put it into a .o file, and then you can relink it very quickly. So you don't have to fully recompile your entire project every time. And that's in fact the subject for the next set of slides. So yeah, and you can do all this by hand, and it's really annoying to do it by hand, and that's why Makefiles exist. So you could do it by hand though. So you could G++, G++-C, Makeowen.cc, main.cc. You can do them all by hand. That generates a .o file. And once you have all the .o files, you can compile all the .o. You can link all the .o files together. Python doesn't have any compilation at all. So how is this different from Python? Python doesn't do any of this. Python is an interpreted language, which is why it runs 10 times slower than C++. And so you could do all this by hand, but we use something called a makefile. And there's different options for makefiles. CMake is really big right now. CMake is big, and there's other options as well. But what I've given you for this homework assignment is the boring, basic makefile that will build your project for you. Okay. And so when you're going to be compiling your homework assignment, you're just going to type make. Okay. Make. And then what make does is that it goes through and says, okay, so we need main.cc turned into main.o. We need imagine.cc turned into imagine.o. We need complex.cc turned into complex.o. And so the first time you build your project, it does all of these steps for you. And then it takes all three of these .o files and makes a.out out of them. Now, imagine all you did was edit this file here. You don't need to recompile any of this, Miss Crump. So if you've got 50 .cc files, once you've got them compiled once, you don't need to compile them again. The only thing you need to recompile is the file that you changed. So if the only file you changed was imagine.cc and you type make will take imagine.cc, make imagine.o out of it, and then relink everything into a.out. So let me show you what that looks like on the server. So if we go into imaginary homework.reference, yeah, if you've already built your project, it won't do anything. A.out's up to date. But let's say I come in here and I edit, I don't want to give you the answers. Homework, I'll just do the original one. So let's say I come in here and I type make. The first time you build it, it has to build the whole thing. So it's going to be slower. It's going to be slow the first time you build a project, right? So it compiles, do you guys see that? It compiles main.cc, compiles complex.c, it compiles imaginary.cc. And it makes, if I ls, look, so before I had these files, now I've got complex.o, I've got imaginary.o, I've got main.o, and if I try building it again, you're up to date. And if I were to try editing imaginary.cc and I don't know, let's do the constructor. Let's say coif equals 0. Right. That's all you guys have to do for the default constructor. I'm giving that one to you guys for free. So save. So I have edited imaginary.cc. I do not need to recompile anything except for imaginary.cc. So rather than rebuilding my entire project, and you know, if you've got 50 different source code files, this can, or 100 or 300 or 1,000, this full recompile can take a really long time. Watch what happens if I type make. If I type make, all it does is recompile imaginary.cc. It looks at the timestamp on it and says, "Oh, you modified that. You modified that, so I'm going to recompile just the file that you modified." And then it relinks them together into a.out. Okay? So as long as the CC file is the header file is included when you type make, it'll compile, yes. And so whichever file you edit, that's the file it'll recompile. It will not have to recompile all 500,000 .cc files. It only will recompile the files that need to be recompiled. Okay. So this, like, if you're working on any large project, they will be using some sort of makefile. And like I said, there's different options other than just make. CMake, like I said, is very popular these days. But what does it look like with an error? Okay, so let's go back in there and let me break the code, right? Coif equals semicolon. If I type make, it'll try recompiling just that one file, right? And then it says in constructor imaginary error expected a primary expression before the semicolon. So you're missing something important. You're missing an expression. An expression could be like 3 plus 5 or anything. Anything that can go within parentheses is an expression. Expected a primary expression before the semicolon token. Token is a symbol, I guess is the best way of putting it, that compilers look for. So, yeah, and yeah, if you try compiling it again, then it'll keep spitting out the same error because I haven't changed it. If I delete that, compiles is fine. Won't run right because there's no actual code in most of this, but okay. Do you have to make your own makefile or does it come standard? Oh, you have to not make your own makefile for this one. I gave you a makefile. I gave you a makefile for this one. In real life, you make your own makefile, and this is a very not good makefile. Maybe is the best way of putting it. It's very basic. It's too basic. Makefiles get a lot better than this, but this is. I made this one because it's your first makefile you're going to see. It will it will make the principles known to you. Make it compile the long way. Okay. Make clean. Make. There's the long way. Okay. So make clean erases all the .o files and erases a.out. So if you do make clean, it wipes it, and then you can do a full rebuild. Or if you want, you do g++ star.cc. But don't. That's what make is for. make is there to automate your build process. Is .out equivalent to exe? Yeah. So the default executable name is a.out for Unix. And the reason for that is because there used to be an executable file format called a.out. And so if you compiled something and you didn't give it an executable name, then it would default to a.out. And so the reason why I still use a.out is because it makes running the results of a program easier, because you don't, like most professional makefiles will do this. .o imagine something like that. The .o means that's the executable name. So if you do that, you see that. So now there is no a.out in this directory. The executable is called imagine. And so the reason why I don't do that is because I have an alias set up where all I have to do is type A to run the program. And if every project I work on has a different executable name, then my alias doesn't work. And so when I do like a professional project, I don't have the executable named a.out. Hell no. But for development work, it's just easy to just have it be the default because I have a single letter alias that will run it. And what happens is that every time I build something, like when I work with other people's code, I build their code, and then I type ls, and there's like 5 different executables, and I'm like, I don't know which one I'm supposed to run, you know? And so you have to, you know. So, no, I almost erased something. Okay. And so if you want to give it an executable name, dash lowercase o is how you do that. And that's proper. It's good to do it that way. It's good practice to do it that way. Okay. So trying to understand the routine eclipse in the command line. It's all the same thing, really. It's all the same thing. In Windows, they call it .exe files. Yeah. Linux does not have an executable suffix. So .out doesn't mean .exe. Linux does not have a suffix for executables. You can just call it Bob and run Bob. Again, Windows is based on DOS, or its legacy is from DOS. And so .exe, the 3-letter suffix meaning executable. Okay, so when you type make, it looks at, there's a web of dependencies, right? So if we come back over here, main actually depends on complex, and complex depends on imaginary. And so if I were to edit, let's say imaginary.h, then that's going to trigger a recompile of complex and imaginary. And if I touch complex.h, then that's going to trigger a recompilation of main and complex. What does touch do? Touch is, it updates the file, the timestamp. So it appears as if the file's been edited. So touch is used to make it look like you edited a file. And so you poke it, and then it'll trigger a recompilation on it. Soft touch, hard touch, yeah, we talked about that yesterday. The counselors at our school at a staff development day told us when it was appropriate to soft touch students and hard touch students. And most of the professors in the audience were going like, I don't think we should be soft touching or hard touching our students. It seems like a bad idea. Yeah. What it means is a soft touch is when you email them, and a hard touch is when you call them into your office hours. But I was just like, I would just pick different terminology for that. You know, like I'm not very comfortable with this terminology we're using here. You wonder if they did it on purpose. I don't know. It's memorable. You know, it's memorable. It's true. Good touch versus bad touch. Now, both soft touch and hard touch are good, apparently. If only there was vernacular for emailing somebody. I know, right? Yeah, that's a soft touch. Wiener's attack, yeah. Memorable in the way that friends can see your privates, yeah. So in C++, you know, you've got member variables and member functions, and the only people that can see your members are yourself and your friends, right? That's what the friend keyword does. So where was I? When are we going to start killing children in C++? How to kill children from a fork? You know, yeah. Get on the FBI watch list. Sure. Okay, so fork parent and kill child. Yeah. Yeah. There's a lot of that. So yeah. So what make does is it looks at when the timestamp gets updated. So if I were to touch main.cc, it would only recompile main.cc. If I were to touch both main.cc and imaginary.cc, if I edited 2 files since the last compilation, then it will compile 2 files, right? Make figures out, this is what make does. Make figures out the minimal amount of work necessary to recompile your program. And that's nice because it speeds up your compilation times. Okay. Excuse me, what? Yeah. So forking is it's a thing in computer science. It duplicates a process. And so it creates a parent and a child process. And so a lot of people Google how do you kill a child, from a fork. And then you get put on the FBI watch list, right? Okay. So yeah, so basically what you guys are going to be doing is you're going to be using Make for this, and for any big project, you're going to be using Make or a similar tool. Okay. And that's why we save those .o files. Those .o files are the results of the previous compilations, and as long as you haven't updated the source code, you don't need to update the object file, and they sit around and they basically save the results of your compilation so you don't have to do them every time. You guys with me on this? Does that make sense? Do you understand why you keep .o files around? They're basically the results of the compilation, and you just don't have to repeat. You don't have to repeat your work recompiling it every time. Hey, Tristan Myers is here. You're scared to do research for this class now. Nice. Okay. So there's a lot to learning Makefiles and a lot of neat things we can do with them. So Visual Studio uses NMake. Like I said, CMake is a thing. There's a lot of different tools, but the basic format of a Makefile is this: target, dependencies, tab, and how to make the target from the dependencies. That's the file format for a Makefile. And so what it does is it creates like a dependency graph, right? So it says a.out depends upon these three files. Okay, well, how do I get this file? How do I get this file from these three files? Well, you run this command here. Okay. How do I get that file? How do I get main.o? Well, main.o depends upon main.cc and complex.h. How do I get a main.o from this file? Well, you type g++-c main.cc. Cool. Complex.o depends upon complex.cc, complex.h, and imaginary.h. So what that means is that if imaginary.h changes, then it will have to update complex.o, and so it'll run this command. And if imaginary.h changes, it'll see how this guy is also dependent upon imaginary.h, so it'll also rerun that command. But because main.o is not dependent upon imaginary.h, it will not recompile main. Okay. And then it will finish up with a link step where it relinks everything together. And so this is a dependency tree. It's a dependency graph. And so if this file changes, then it will just rerun this and then relink it. Okay, that's the file format for Makefile. And if you're like, wow, that's a weird file format. What, did somebody like hack that together in half an hour and then go on vacation for a month? And the answer is yes, that's exactly what happened. The guy who made Make needed it to automate the build process at, I don't know where he was at, IBM or something like that, back in the 70s or early 80s, something like that. And he just kind of hacked this thing together and went on vacation. And when he came back, everybody in the company was using it, so it was too late to change the file format to something reasonable. And so we still use it today. So don't go on vacation, I guess. I don't know. But Makefiles get to be very interesting. They get a lot better than that. Moral of the story is no fun ever. I don't know. My first real job, I worked there for a week and then went to Puerto Vallarta for a week. Yeah. So this is like this is actually a pretty nice Makefile here, actually. So Makefiles can set variables, and so if you want to change what compiler you're using, you only have to change it in one place, right? So if I want to switch off from G++ to Clang++, the Clang compiler, all I have to do is change it there. And then rather than, see in the Makefile I gave you guys, you see how it repeats G++ every time. I'd have to change it in every place. Whereas with a real Makefile, it uses a variable, and then you can change the variable. And then the flags are the different compilation options like what version of C++ are we using? This is C++ 20. Turn on all warnings. You would think that all warnings means all warnings, but it doesn't. If you actually want to get all warnings, you have to turn on all warnings and then turn on extra warnings on top of all warnings. But that's actually not all of them either. There's also everything, warning everything, which turns on even more warnings than all and extra all warnings. Super duper big warnings, yeah. That's the version of C++ we're using, C++ 20 in this case. That says turn on debugging information. That says turn on the optimizer at the highest optimization setting. So, so you only have to set those flags once rather than having to copy and paste them onto every line, like in the basic Makefile I gave you guys. And then there's even more cooler stuff where this says set a variable equal to all header files in the current document, set a variable equal to all CC files in the current document, create a rule to turn all CC files into .o files, and to make a .out, you compile all the .o files together. To make a .o file, you compile the .cc file and any header file. So this will actually compile an entire project, a pretty sort of an automatic Makefile. As long as you're not doing anything weird with your source code and things like that. This will basically, if you've got 50 .cc files and 50 header files, and you edit one of the .cc files, it'll figure it out and recompile it. And this is kind of a generic go-to default Makefile that you can start with and take with you for all of your Makefile needs, and that's located here. So that's a more usable Makefile than what I gave you guys. This is a even simpler one. So you can either compile debug or compile release. If you type make debug, it'll compile the code with all the safety options on. The debug library turned on, the debug standard library turned on, address sanitizer turned on, undefined behavior sanitizer turned on. So it adds like 4 extra levels of safety and slowness to your code, turning it into Java. But if you want it to run quickly, then you can define release, which turns off asserts and turns the optimizer on, turns off debugging. And so typically you'll do something like that to when you're developing your code, and then when you're ready to release it to the public, you compile it in release mode, and it will get a lot faster. It'll get 10 times faster from that, if not more. So there's a lot of things you can do with Makefiles. They're a whole, like, you can buy books on Makefiles and things like that. But these two things here are 2 examples that I made for you that will kind of be everything you need. The one in your current homework assignment is serviceable for this homework assignment, but it's not how people really do Makefiles for real. Okay, so here's an example Makefile. So take a look at it, and let's say I've already built the project a few times, everything's going, and let's say I edit complex.cc and save it, and I type make. What 2 lines of what 2 commands are going to run? So let's say I just edited this file here, complex.cc, hit save, and I type make. What 2 lines are going to run, and in what order? What do you guys think? I just edited complex.cc, I type make. Make says, okay, complex.o is dependent upon complex.cc, main.o is dependent upon main.cc, a.out is dependent upon main.o and complex.o. And so there's this dependency web, dependency tree. Okay. And so if I just saved and updated the timestamp on complex.cc, then the first thing it needs to do, because it looks at the timestamp of this guy. Let's say that guy was edited like last Tuesday, and this guy was edited on Wednesday, right now. If this guy's more recent, then we need to do something. We need to bring complex.o up to date also. It uses timestamps to do this. And so how do I go from complex.cc to complex.o? It will execute this command right here. So the first thing you'll see it do is say g++ -c complex.cc. And that will generate a new complex.o whose timestamp is now, now on Wednesday. And yeah. And then as long as we don't edit complex.cc anymore, it will never run this command again. It only runs a command when something on the right-hand side is newer than the thing on the left-hand side. It checks the timestamp here. This one is, the main.cc is older than main.o, so no problem there. Oh, but look, complex.o, that's now from Wednesday. A.out was from Tuesday. So we have something newer on the right-hand side here than on the left-hand side, and so it will execute this command as well. And this will now make a brand new A.out from now. And it's actually much more fine-grained than Wednesday, right? It's like Wednesday at 1:59 and 23 seconds or something like that, right? And so every time you save a file, it updates the timestamp on the file system. And if ever anything on the right-hand side has a newer timestamp, like if this one was compiled at 1:58, and this one was compiled at 1:59 and 23 seconds.
Dad, I just found out, you know how...
Then it recompiles. Yeah.
When I was a baby, I used to say la. In Arabic, that actually means no.
La means no. Interesting.
In Arabic.
That's interesting. Yeah, when my daughter was a baby, close the door, girl, thanks. She didn't actually cry when she was 1 month, 0 months old. It's the weirdest thing. She never cried. She would go la. So when she was there's Ada. Yeah. She'd go la, la, la. And you couldn't even be mad because it was just like, you knew she was mad about something, but she wasn't like crying. She was just going la, la. So it means no apparently in Arabic. Okay, so do we need to do imaginary.o or complex will create automatically? The Makefile will make them for you. So when you type make, it will generate these .o files, and it generates them using this command here and this command here. -c means partially compile. It means make a .o file from a .cc file. Okay. So you should not be editing the .o file. You don't do anything with it. Just leave it there. Just leave it there. And some Makefiles will actually create a separate directory. So it's fairly common for a project to have like a source directory. Like you'll have a project directory. Let's see if you guys can see that. You can't see that. Okay. So it's pretty common to have a setup where you'll have like your project directory, and then inside of your project directory you might have one directory for headers, and then another one for like server source, and another one for like client source, like if you've got like some sort of client server game or something. And so you'll have like 3 different things, and then a lot of times we'll have a separate directory for like object code. And so when you generate .o files, it dumps them all into this directory over here, just so you don't have to look at them. Right, so you'll have all your .h files over here, your .cc files for the server here, the .cc files for the client over there, and then all the .o files. Some Makefiles will just toss them off into a different directory, and you don't have to see them. Because when you type ls, you don't want to look at all the .o files, because you don't do anything with them. They're just cached results of compilations, and so you technically, like some people will get upset if they see that .o file there. Belongs in a museum. It belongs in a different directory, and that's fine. That's fine. You can, like I said, you can make your Makefiles as complicated or not as you want. Is that Kearney? Yeah. For some reason, the only emoji of me on the ACM Discord server is me frowning, which is something that I don't really do very, very often. But there is Tristan. Yeah, there's Tristan's face right there. I was going to post that. I think I took that. Yeah, I took that photo, Tristan. We were at some pizza place in Clovis, and Blast and Brew. Yeah, yeah, that was a fun time. It was a good time. Great photo, Tristan. Okay. In and out. All right. So, yeah. So if you want to change the name of an executable, it's fairly common. Like, it's good practice, honestly. The reason why I don't do it is because I'm just used to. I have a workflow, right? And my workflow involves hitting A to run the thing. I edit things quickly. I compile them quickly. I run them quickly, and anything that interrupts my flow, I don't like. I've got most of my things. I've got most things aliased. So if you want to see all the different aliases I have a lot of aliases set up. And so rather than typing make, which is 4 whole letters, 4 letters, that's way too many letters. I have an alias set up for MK. And that clears the screen and makes it. So, so many compilation errors will appear at the top of the screen, which I like. And then to run it, I type A. So, CC VV. Anything that I can do to make my typing go quicker, I do. If I ever find myself typing something over and over again, then I alias it. And so if I have an alias for a.out, then it won't work if the executable is called calc. Like I said, this is good practice. Most Makefiles you'll find will set an executable with a different name than a.out. It should be. But for just like my personal workflow, that's how I do it. What command is aliased as VV? VV means VI vim the last file that you vimmed. Vim the last file that you vimmed is VV. So if you're doing a lot of work, VV takes you back into the last text file that you ran. It's set to run the last command that began with VI. Yeah. I mean, how to write it? I want to add it to my CSI 26 terminal. Oh, if you want to see all of the aliases that I've set up for you guys, well, actually, you don't even have to do that. If you want to look at your .cshrc file, there's an alias for that. I have an alias set up for editing your .cshrc file, which is where all the aliases are, and it's called VC. So type VC, and it will open up your .cshrc file, and you can see all the different aliases that I have set up. Some of these, like the sudo stuff, you probably, I think I took that out of yours because you don't have sudo access. You have no power here. These also you don't need. But yeah, alias A to be a.out, alias VI to be vim, alias V to be vim, alias VC to be vi.cshrc. So if you're into like Unix hacks and things like that, type VC and enjoy. My .cshrc file is something that I've built up over, almost 30 years now, and there's a lot of the muscle memory is so great. I always type VV, then it tells me it doesn't exist. Yeah, yeah. It's a workflow thing, and I really don't like wasting time when programming. When I'm programming, I want to be as efficient as possible. Part of that is because I used to do programming competitions a little bit, and in programming competitions, you're on a time limit. You have 3 hours to write 6 programs, and the programs are not trivial programs. They're not trivial programs. There's usually 2 easy, 2 intermediate, and 2 hard, and even the easy ones like require thought and things like that. Like one of them is given the layout of an apartment building, tell how you can move a couch through it. So you can move the couch, or you can rotate the couch. But like if the corridor is like this wide, you can't rotate the couch, and so you might have to walk it through and back it up, and and you have to generate a movement pattern for a couch coming through an apartment. And I was just like, I still don't know how to do that. It's like, you can have rooms of different sizes and corridors of different sizes and doors of different sizes, and you've got to give it directions to steer a couch through it. Like, my lord, dude. Yeah, I still don't know how to do that. One that I eventually figured out was like a hive. Like, if you've got hexagons and you've got them numbered from the center one is numbered 0, and then sort of in a clockwise spiral going out, they're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Find the shortest route between two different spots on the in the hive. So from like hexagon 50 to hexagon 42, give the shortest path. And it's pretty easy because they're hexagons, so you just travel in one direction. But how do you figure out where? Because it's a spiral. It's zeros in the middle, then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it spirals out. So it's like, how the hell do you like? How do you know where it is? Like, is there a, I was sitting there like figuring out the algebra on it, and I eventually figured it out. But it's like, it's not immediately obvious. It's not immediately obvious how to do it. And you've got 3 hours to do 6 of these things. And most people did it in pairs. And so you'd have 2 people and they'd split up the programs based on who thought they could do which one. And I always did it by myself. And never won for some reason. But sometimes I would be like the only person to solve a particular problem. And that felt good. When they said only one person solved problem 5. I was like, yes. It's a good feeling. And so as a result of that, I learned how to code quickly. And that's actually a really valuable skill. There is an overwhelming difference in speed and productivity between programmers that are highly productive and like programmers that are not highly productive. Like even in a company, like and think about it, it's weird. It's like, if you look at like professional baseball players, what's the highest batting average in like Major League Baseball? Like in the high 300s, right? So that means a bit better than, a third of the time they get a hit, right? And the average batter is batting about 250, so about 1 out of 4, And so the difference between the best batters and sort of the average batters is not very big. I mean, it's big. It's enough to pay people millions of dollars because you need every edge you can get. But it's, it's not that big a difference. 1 out of 3 hits versus 1 out of 4 hits. It's significant, but it's not as big as it is in programming. In programming, like when I was first starting out, my boss is able to do things over his lunch breaks that like still blow my mind today. Like he made a VR arcade game system during his lunch breaks. So in his time off from programming, he created a virtual reality pool game where you were the pool ball and you would knock yourself around on this table and knock pool balls into pockets, and it turned into a commercial product, and that was just like a hobby that he did while he was working at the hobby, like doing programming while he was programming. And like I needed a font made, so he's like, all right, yeah, sure, I'll do that for you. And so he was just I just watched him. He was one-handedly eating pasta salad, and just he wrote a program that would take mouse inputs, and he just goes click, 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 click. Okay, there's the B, click, 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 click. There's the C, click, 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 click. D, hits a button, dumps it to disk, and then he has a vector graphics font for me. And he wrote the program for that and made all the letters and all the numbers in a lunch break, in like a 45-minute lunch break. He did that whole thing. And I was just like, whoa? How did you do that? And where is he now? So yeah, he was a cool dude. He worked for Facebook for a while. He worked for Zynga for a while. Now he's doing data science or big data in Arizona somewhere. He got his pilot's license, so he flies around for fun in his airplane. Dude's a very smart guy. Really love that guy. He's pretty cool. Sean McIntyre is his name. Really cool dude. And just it just blew my mind. I'm like, what? Because like if you had me do that, it would have probably been a week, to figure out how to enter fonts and all this other stuff. And he just like, yeah, sure, I'll do it over lunch, And so that's something that I try to teach my students, is how to become productive programmers. and how to become big brain, you know, order of magnitude better at programming. So, okay. So, yeah. So basically, for any real project, you're going to build it using Make. You're not going to be using G++ anymore. Cross that out. Yeah. Or you can just use Make, which is my alias that I've set up for. Okay. You can use G++ or compile for single file projects, but for big projects, just type Make. Okay. So for imaginary homework, you're going to have to use the Makefile. Don't include a .cc file. That defeats the entire purpose of it. You know, if you have main.cc, include complex.cc, and complex.cc include imaginary.cc. At that point, you might as well put them all into a single file, right? Because that's what you're doing. You're including everything into one file, and that's fine. Just make sure you delete the Makefile. Some people do this. Some people will actually do this, and they just have one file for their whole project. And even if it's split into different files, they include them all together so it becomes one file, and then they compile it that way. And that's it. Sometimes it's actually faster that way because it might sound a little counterintuitive, but if each of these guys is including like 500 different header files, then every time you compile them, you have to go through 500 header files. And so if you put them all into one file, then you only have to go through these once. And so sometimes in weird situations like that, sometimes it is actually faster to do it this way. But in general, no. The whole point of doing an include is to speed up compilation times. And so you include header files only. Because header files are small, CC files are big, and so main.cc should just include a header file, not a CC file, for the speed benefit. And then it'll get linked together at link time. Can you parallel run? There are parallel build tools, yeah, where you can compile each of these files separately. Yeah, they exist. If you have multiple CPUs, then it's fairly common to have each CPU core compiling a different .cc file at the same time. Yeah, absolutely. That's one of the reasons why Microsoft always buys the very best CPUs for its programmers. If you work at Microsoft, you get a brand new Core i9 or Xeon CPU, PC, 3 monitors, 32 gigs probably of RAM. I don't know what the specs are right now, but you get top tier equipment every year, every 2 years, and the reason for that is because all the time that you're sitting there waiting for your code to compile, you're paying these people $200,000 a year, and you're paying them to be sitting there. Right? If you have a programmer, a very highly paid, expensive programmer, I think the starting salary at Microsoft is like 130 or 150, but by the time you get up to like a senior lead, which is not that hard to get to, you're making 300-ish, a year. And then if you become like a partner or something like that, you're talking $500,000 or $1 million once you get into the upper echelons tech. I don't remember what the actual term is, but they have different titles and things like that. You don't want to be paying these people to be sitting there staring at code compiling, right? Paying $4,000 or whatever for whatever the absolute very fastest computer is, pays for itself very quickly, right? Pays for itself very quickly because you've reduced the downtime of your very expensive programmers. But will it run Crisis? That's the question. Dual 3090s, yeah, if you can find them. Yeah, the money is decent in computer science. Money's decent. The money is decent. When I was running my own company, I was making comfortable 6 digits and I didn't have to work for other people. That was nice. That was nice. I liked my own boss, me. But yeah, the Google, Microsoft. Once you start working your way up the hierarchy, they pay recent, like, pretty well. Pay pretty well. It's a whole talk we could probably give on that, but you can go onto websites like Glassdoor. I forget the name of the one website where it shows you the pay scales for the different companies. Here's Amazon's pay scale, Microsoft's, Google's. Microsoft has a leveling system, so when you get a job at Microsoft, you have a level. It's like in a role-playing game.
What happened?
You just went to the next slide, girl. Yeah, I think we're good. Oh yeah, if an error occurs, output -1 and quit. Don't output bad input, output -1 and quit. Okay. Yeah, and so like basically, I'm a level 65 programmer at Microsoft, and then you get XP. You literally get XP for doing different things. Like documentation is one of the XP bars you can level up in. Writing code is, and they cap out. And so basically, it's designed to encourage you to not just write code, but also to document your code, which nobody wants to do. So if you want to get promoted, you have to write code, and you have to document your code, and you have to go to meetings and communicate with people and send emails and stuff like that. And so you build your XP bars in these 5 different categories, and then you level up, and you get a nice. Now I'm a level 67 programmer at Microsoft, and everybody gets paid the same amount basically based on the level that you're at. You're only level 66, noob. So yeah, and so like if you want to optimize your promotion, then you look at the promotion requirements and you actively go after the areas. Hit discard, yeah. So documenting code, yeah, like basically writing documentation for it. Like this is how you use this code. If you wish to use this code, here's step 1, step 2, step 3. This is what this function does. Here's a diagram showing how all the different pieces connect together. Yeah, commenting code obviously is documentation. And so each of the companies has their own weird twist on advancement and things like that. Google, I know for years, did stack sorting. So all the people in your team would be ranked from best member of the team to worst member of the team. So it'd actually be really bad for you to work with good coworkers because you'd be at the bottom, right? And so you'd want to find a team of dumbasses, sorry, because then you could be at the top of that team and you get promoted, right? And so various companies do stack sorting.
But what about everybody's know what you know and everybody doesn't know what you don't know?
Yeah, well, I mean, if your team fails, then that's also a problem because Google, you get promoted also based on released products. And so if your product gets canceled, sucks to be you, you know? And so there's some serious issues with how, like, Google does promotion and advancement and things like that. All of the tech companies have their own weird twists and quirks and things like that because they're all kind of competing after the same talent pool and they're trying to recruit people. But also they want to promote people that do good work. But at the same time, you do good work, and then your product gets canceled due to no fault of your own. And then it's like, great, I spent 2 years working on something. And Google is notorious for this. They'll start a project, then cancel it. They'll start a project, then cancel it. They'll transfer people onto a project, then cancel it. And so you could be there for 10 years and never release a product, you know, because the managers are having the problems, not you. And then you don't get promoted ever. And so... you know, it's an issue in the field, you know. So, they thought you were gonna write Dio. Yeah, yeah. Documenting code's not bad. Honestly, a lot of programming, like when you work as a programmer, isn't actually programming, right? A big part of it is communicating with people. Computer science is a very social endeavor. You'll have your Slack channel open and everyone's talking on it. That's why I have you guys do pair programming. It's because you need to get used to communicating with people. Like I said at the start of class, does anybody need a partner? Or has anyone's partner flaked on them? because I've got one student right now who's looking for a partner, and we'll match you guys up. Anyway, I'm going to stop the stream now, but I'm going to hang out for a little bit, and we can talk about GameStop and all that other stuff.